Yes, recording started. And yesterday, in the last class, Nabil has to continue with the number system. Yes, Nabil, you go ahead, Nabil. Once Nabil is completed, then fourth batch has to continue with the recursion and the error propagation. Yes, Nabil.
Yes, sir. Hello everyone. Today I'll be talking about 2's complement method, the signed integers representation. So basically, in the earlier days, what happened in 1950s, mainframes were introduced basically, and during that time, the sign and magnitude method was popular. And the sign and magnitude method had some limitations. Mainframes were very huge, so we need to reduce the hardware dimensions and all.
Yes, someone you verify whether the recording for me it was started, but the counting not yet started. Someone you please cross check with your system and you let me know.
So it is started, sir, recording.
Okay, go ahead, Nabil.
So in the earlier days, mainframes were introduced in 1950s. During that time, sign and magnitude representation was popular. And sign and magnitude representation had some flaws. The hardwares were very big. Mainframes were very huge computers, so it was difficult. So to reduce the hardware dimensions and to decrease the cost, they introduced the ones complement method. And to further decrease the hardware parts and decrease the number of transistors, they introduced the 2's complement method. So next slide. Nishan, next slide. So what is 2's complement method? So to get the 2's complement method, we'll find the ones complement of the number and we'll add 1 to that. So for example, we have a binary number 000 10 100. So ones complement will be 1110 1011, and we'll add 1 to that. So we'll get this 1110 1100. This is the 2's complement of the number. Next slide. Next slide. Subtraction of a smaller number from a larger number. So to subtract a smaller number from a larger number using 2's complement subtraction, we follow these steps. We'll find the 2's complement of the smaller number. We'll add it to the larger number, and whatever carry we are getting, we'll get carry all the time. The carry will omit it. Next slide. So for example, we have this number. We have to subtract 1010 base 2 from 1111 base 2. So using 2's complement method. So the smaller number among these two is 1010. So 1010 will find the 2's complement of that number, and it will be 0110. Then we'll add both the numbers. We'll get carry at the end, like 1 will get carry. So we'll omit that and we'll get the answer as 0101. Next slide. Now subtraction of larger number from smaller number. So to subtract larger number from a smaller number using 2's complement subtraction, we follow these steps. Same thing, we'll find the 2's complement of the smaller number. We'll add it to the larger number. Here you will not get any carry. And the result is the 2's complement form and is negative. So we have to find the 2's complement of the result and we have to put a negative sign because we are subtracting a larger number from a smaller number from a larger number. Next slide. So example, you have same example 1010 base 2 from 1000 base 2. So we'll find the 2's complement of 1010 base 2. So it will be 0110. We'll add it to the larger number 1000 base 2. Then you will get 1110. Now we'll find the 2's complement of this number, which will be 0010. Now we have to put a minus sign because we are subtracting a smaller number from a larger number. So we'll get minus 0010. That's the answer. Next slide. So difference between 1's complement and 2's complement method. So 1's complement, it is basically inverting. Zeros will convert it to ones and ones will convert to zeros. Basically in gates you can say it as the NOT gate. this converting zeros to ones. And 2's complement method, first we'll find the 1's complement, then we'll add 1. And 1's complement method, it requires two operations like converting zeros to ones and ones to zeros. In 2's complement method, only simple arithmetic operation. You will find the 1's complement and you will add 1 to that. And 1's complement, it is often used in logical manipulations for inversion operation. And 2's complement, it is basic algebra, like arithmetic operations applications we have seen. Next slide. So why do we prefer 2's complement over 1's complement? So in 1's complement method, like 0 has two representations. So to increase the range, we are using the 2's complement method so that we can decrease the negative 0. We'll keep only positive 0 and we'll remove the negative 0. And 2's complement will allow negative and positive numbers to be added together without any special logic. This means that subtraction and addition of both positive and negative numbers can all be done by the same circuit in the CPU. Like CPU has two units like ALU and the control unit. So everything will be done by the arithmetic and logic unit. If we use 2's complement, there will be no part for the control unit to play in this case. And another advantage is 2's complement doesn't require any carry value. So the carry values will omit basically. Next slide. Thank you. Thank you, sir.
Yes, Nabil. Thank you, Nabil. Yes, fourth batch, you continue with recursion and error propagation.
So I'll be starting with recursion. Just a minute. So is my screen visible?
Yes, yes.
So hello everyone. I'll be covering recursion. So basically we'll be covering what recursion is, why we study or read recursion, and how do we encounter recursion in our day-to-day life. So basically recursion is a very simple concept in programming, yet it is one of the most mathematically elegant and mesmerizing universal concepts. We see recursion in natural things a lot. Like we see it in sunflowers. The bud of sunflower follows a Fibonacci sequence, like as seen in the picture. And many plants follow recursion. We see recursion in food as well. Like in the first picture, a pizza with pizzas as toppings. That shows recursion. And in the second picture, it shows a recursive pizza, which was actually supposed to be hypnotic, but now it is making me hungry. So we'll continue. Let's get to a formal definition of recursion. Formal introduction, I mean. To understand recursion, one must understand recursion. This is not exactly the formal one, but we'll proceed to a formal definition. A recursive function is a function that calls itself. It can be a void function or a non-void function. What Google says is recursion is the process a procedure goes through when one of the steps of the procedure involving the procedure itself. A procedure that goes through recursion is said to be recursive. If we define a function as recursive, it is basically calling the function again and again and again. So that's recursive function. So structuring of a recursive function. Every recursive function can be described as having the following structure. It has basically two concepts. One is the base case, where when we do something immediate, when the input is as simple as possible, we don't make a recursive call. But in the recursive case, we simplify the problem and thus we make a recursive call. So these are the two concepts. We'll be seeing some problems. So the first problem here it is the Fibonacci series. So the mathematical equation here is given as follows, which you can have a look. So the recursive relation here it is Tn is equals to Tn minus 1 plus Tn minus 2 plus the first initial function. So you can have a look at the working. It is self-explanatory, so I won't explain that. Similarly, the second problem is of to find the factorial of n. Everyone knows factorial, right? So the recursion relation is Tn is equals to 1 for n is equals to 0. So Tn is equals to 1 plus Tn minus 1 for n greater than 0. And here is the working of the problem. Similarly, so uses of recursion in NME, like numerical methods. A huge variety of numerical methods rely on iterative methods for obtaining results and hence end up recurrence relations to get the job done. Few of the recurrence relations we have encountered during this course are Newton-Raphson method, which we have studied recently, and Liebman iteration method, which we have studied. So now Sanjay will continue with the second part of recursion.
Is Sanjay? From I think there is a network issue with Sudesh Gaikwad, and ask someone to present Sanjay, or from your end you present the PPT.
So can you see my screen? Like is it visible? The percentage.
I think it is, yes, now okay. You start your presentation.
That's it. Okay, guys. Hi. Like Siddesh said, he explained the beginning of recursion. Now I'm going to explain it clearly. So how recursion works and how it's divided. Like recursion happens like in tree and stack method. It's used both methods. And I'm going to talk about less about dynamic programming. Let's see why I'm going to talk about dynamic programming. Okay. So recursion tree. You all know basically how tree looks like. There are stem branches which divided into much smaller sub branches like that. Recursion tree is also divided into it's a pictorial representation of a problem which divided through nodes and expand broadly as we go below. And the second term of its in recurrence is known as roots. It's basically a divide and conquer algorithm. For example, let's take our current scenario. Sir has a problem of every student of this class to make a presentation. So what he did, he just divided the group of, there are 34 students. He can't just go and ask each students to create a separate presentation. It would be much difficult process for for him to guide each and every student. So we divided the students into 6 groups, where the group member itself discuss among themselves and come up with the ideas to solve the particular presentation or particular problem. Then in that particular in one presentation, for example, let's take my presentation. We divide the parts into two parts: recursion and error propagation. In which each in recursion, 3 members took and divided into 3 parts, and similar in error propagation. Like that, there will be all 6 groups will work simultaneously like that, which results in a much easier process, and so the time would be less compared to presenting each and every student alone. Okay, so it's like a process. You can understand, right? Then this is now let's go to a complex problem. There's a Tn is equal to 2t n by 2 plus n square function. We need to use recursion tree method. Here in this we divide n square into 2 sub branches. Let's take a sub problem, and it divided into t n by 2 and t n by 2. Simultaneously, it's divided like a branch, like a root. How it works? Okay, like if in a tree, if the roots, how broad the root is, the tree gets much nourishment. Like that, the branch is much bigger. Then the solving the problem would be much easier. Like after dividing that into branches, then we have to sum it up. Tn is equal to n square plus n square by 2 plus n square by 2, and we are using summation and formula. You know this formula, summation formula, and we are getting Tn is equal to theta n square. This is a basic, like it's not it's a simple problem. It's not a complex. There are some complex problems also. Like for example, for your understanding, I'm using the simplest problem. So here comes the SAT recursion, a recursive stats. Okay. So in previous problem, I said the branches. There are branches. Okay. So each branches main program. Then it's divided into branches. Then that branch is divided into sub branches and goes on. And if you look at the same process is getting repeated. Okay. Like n is divided into 2, and n square by n by 2 square is divided into n by 4 square, and simultaneously goes on. This is a process of stuff. Like if you write an algorithm or some program for this, you might be using the same process repeatedly. You will understand it with the example. Like I'm going to give you with an example. Let's see. Okay, you might ask, you might think, why stat? Why do I need this? Because that's what I'm going to explain. Like I said previously, recursion is and like Siddesh said, it's a process that repeats time again and again and again. It's like a loop or a cycle of chain of cyclic chain of a function calls. Okay, so whenever your function is called, a nested function is called, or return the value, then the other function is the same similar function is being called again, and it returns the function. It's like the start and return of a function calling. It's like an analogy to a push and pop of operation of stats. Okay, it's like a mimicking process of that. So the process will be like you're calling a function and using it. Using the function, you're again calling the function. It's like I will explain it much bigger with an example. See here. Here is the function. Here is smaller number is equal to n plus sum of n minus 1. Okay. In first function, it's the same similar function. Okay. So we are initiating n is equal to 1. Then we are calling the function smaller sum function, and we are getting and now we are initializing n is equal to 2. Then we get a smaller sum. Then we are again calling the same function Again, so, for 3, it's like in a Fibonacci series, we will add, right? 1 plus 1 is equal to 2. Then 2 plus 3 is equal to 5. 5 plus 3 is equal to 8. It's like the single function itself repeating. So it goes on, and we can use for a much complex problems, and it would be easier if the process is recursive. You don't need to do every time some. You can use a recursion method to finish it up easily. Every new method has some disadvantages. Okay, so the disadvantages of recursion is the process is slower. Okay, for example, if you want to find the nth term or 100th term of Fibonacci series, then the process would take longer. Like in recursion method, it would add first 1 plus 1, then 1 plus 2, 2 plus 3. Then it would take long time to process, and it consumes lot of memory. Okay, so and if the program is much complex, like it's a simple, like for a Fibonacci series, it's a simple sequence. You can analyze it and understand it easily. But when it comes to complex programming, like for a game, in a game, you need to do. There are for a like take PUBG, there are multiple actions. There is multiple predictions and all. You can't use a simultaneous process there. Okay, if a guy is running, it means he might be changing directions, and there will be infinite choices and possibilities. You can't make recursion useful there. It would be complex, much complex. So, and it would be time consuming, and it's consumes a lot of memory. Okay, so to overcome this, if the default by human nature, if there is a disadvantage of a method, then people will try to come up with a new method which overcomes this disadvantages. Now, Richard Billman found a new method that's called the dynamic program. So you ask me what now you know why I'm going to introduce dynamic programming. So dynamic programming basically uses the principle of optimality. It's like if you ask optimality, I will say you in a bit. Like what dynamic programming do is it will the program will start from the goal instead of starting with the question, it starts from the endpoint, from the solution, and it goes way up from bottom to the question. While throughout the process, there will be sub solutions and the divisions of each and every program, where you might find different possibilities, different choices, and different format also. So in that different choices, possibilities, and formats, programming helps in finding an optimal, like easy way to find a solution from the question. I will explain you in a bit this diagram, the principle of optimality. There's a start point and there's goal. Okay, start point and goal. So there are 3 ways to solve this problem. Like you can okay, 3 way. I will go with another example later. So start and goal. So if you add this way, like how much distance it would be? 2 plus 5, 25. It would be 27, and 11 plus 70, it would be 28. And if you add a root A, then it would be 5 plus 20, 25. So among this, which would be the shorter one? So the first one, the A path will be shorter one. Which is the shortest path? It is called as optimal solution, because there is not much solution, much easier solution than that. So this format is the format that the dynamic programming uses. So it would be easier. Solving a program would consume less time and solution easier. I can show you and I can tell you another much simple example. Everyone uses Windows, so everyone knows the operating software. If you want to go to local disk C or D, there are many ways. The simplest way is just go to taskbar and click File Explorer. Then the File Explorer will pop, and you just go to local disk C or D. There is another way also. You have to go to Start button, and you have to type File Explorer or this PC, and you need to go to, and you need to select that, and you need to the File Explorer will pop up, and you need to select local disk D. And there is one more too. Then you, if your desktop default as this PC, you can go that also. That's also. So in this case, there are two optimal solutions. One, by clicking one click in the taskbar. Okay, File Explorer. That's one solution. Or else you can go to desktop. If you have this PC in desktop, then one click, the local disk D will be open. So there are two optimal ways. Just you need one click for the process. So this is the simplest format of optimality. There, if the program gets much complex and much bigger, then there will be many optimal ways. Okay, there will be more than one solution, depending on the choices of the user. Like if a user using an app or a specific app software, then yeah, you might have many ways to overcome a particular problem, which solves a specific conditions or something like that. That's why Richard Bellman developed a dynamic program. Okay. So, like before I'm going finishing, I'll just explain you how dynamic programming and recursion works. For in this recursion, just look at the function. It's a Fibonacci sequence, Fibonacci format. The function is in the int form. Its data type is n. So if the function checks out first the values, the input value is lesser than or 2, or if the function is lesser than 2, return 1, or else go to return function fib x minus 1 plus fib x minus 2. Okay. In this, what happens? If you imagine, then what will happen? If I let's type let's imagine x is equal to 2. Okay, the if statement would be false. Then again it will goes to return function. In return function, you're again calling that function, which in that case it would be 2 minus 1 1. Okay, yep, fib 1 plus fib 0. In that case, if you imagine, the function is calling again the same function, then the function will come up, run again and return 1 1. As both of the condition x is lesser than 2, so the if statement is true. It's like the first if state first x is equal to fib 2 still running still, and again you are calling fib 1 and fib 0. So there are at that time there are 3 functions running at similar at same time. Okay, so it would consume lot of memory, which in return, if we default no, if you consume if a program software consumes lot of memory, then it would slow down the system or memory power. Okay, so if for a simple program itself, it consumes more memory. What happens if there's a much complex programming, like whatever we do in dynamic program in a game or not? You can't play a single game like PUBG or something like that. It would be much difficult to run it in a normal mobile phone itself. So it would be much complex. When it comes to dynamic programming, here you see there is an initial function fib result. Okay, so the user would call the subfunction that is below here a void setup. This function is a void. Okay, you need not to worry about this. This function would call this function to result of our final result. Now, in this case, you can see the mechanism. Like here is the input, here is the process, here is the output. It's like a format. Here, in this case, everything is inside a function, but in this case, it's outside the function, which helps in controlling the function much easier. If I let me explain how it works internally. In externally, it looks much bigger than the recursion, but internally, when it comes to memory use, it would be less. Let's see how. Like for by default, we have given fib result 0 is equal to 1 and fib result 1 is equal to 1. Okay. So if you use if statement, in this if statement, the fib result, let's take in this initial value is 2. Okay. So 2, 2, it happens like it goes on infinitely. Okay. 2 minus 1 and fib result 2 is equal to fib result 2 minus 1 plus fib result 2 minus 2. So fib 2 is equal to fib result 2 is equal to fib result 1 plus fib result 0. So it would goes on and get the result and stores in memory. Like in this process, after giving the input only the process happens. But here before the giving the input itself, the process happened. Okay. So it already happened and stored the memory, the required data in its memory. So if we ask for a output, it would give next second. Okay, it will take less a second. I don't know how much nanosecond it will take. Sorry for that. It will take less. It would be faster than recursion. Like it would give instantly because the memory is already stored and the function is already finished. There is no need to worry about this and all. There is no need to worry about memory and all because the function is already ran and it's already stored the memory. The function is ended, so the memory of the function will be wiped. So there is no need of this only single function which already happened and it stored the result and the function is already ended. So there is no memory is used compared to recursion and the process already happened. So if you need it, if you will just get the result, you need not to the process need not start after you giving the input. Okay, you just need to if you want fib result 2, just give I need fib result 2, then it will come the result come instantly. So you need in that case the disadvantage of recursion is overcome. Like the process is much faster than that, and the memory is not. The program is the function is not unnecessarily running. It's already ended, and the required data are stored. So the memory is saved. Everything is done. That's it. This is the process of dynamic programming and recursion. Now, due to some reasons, my friend Pranav can't continue. Now we are going to error propagation.
Good morning, sir.
Very good morning.
Very
good morning, sir.
So I will be discussing the topic error propagation. Sanjay, next slide. So definition: propagation of uncertainty or propagation of error is the effect of variable uncertainty on the uncertainty of a function. In simpler term, we can say that if a variable has an error and we use it in a function, then the error propagates until we see the final result. In the beginning, it may see that the error may be extremely small, but when it accumulates, it may significantly change the result we required. Example, if we multiply two numbers with error, we get a different result from what we expect. Or in day-to-day life, in physics lab experiment 1 in 12th standard, we would have done it. The resistance of a wire, you would have never get a straight line in the graph because there would be an error in potentiometer or an ammeter. Or other example, maybe you can create a small table of 4 centimeter height. When you use measure for first leg 4 centimeter, there may be error of 3.9 centimeter. And when you use the first leg to create the second leg, again the error propagates. The finally, when we see create the table, we can see that it's uneven. Maybe the error in the last leg would be almost like 0.5 centimeter. This is how the error propagates and accumulates to create a significant change in the result we require. Next slide. So uncertainty can be expressed in a number of ways. Absolute uncertainty or absolute error, delta x. The delta x error 0.2, the absolute error. Next. Relative uncertainty, it is delta x by x. We take 0.2 by 2, 0.1. So we can convert into percentage also 0.1 into 100, then 10%, etc. Next slide. So I'll bring you basic formulas for error propagation. In these formulas, we may not get the exact result, but we mostly get approximate. So this function must only contain addition or subtraction operation. When two values add or subtract, the new uncertainty is a sum of individual absolute uncertainty. If y equal to a plus or b minus b, then delta y is equal to delta a plus delta b. Either it's addition or subtraction, the error will always be added. If you see the example 1, t equal to 3.04 plus or minus 0.03 plus 9.08 plus or minus 0.05, we can see the error is added here 0.03 plus 0.05, 0.08. Similarly, in difference or subtraction, we can also see that again the error is added 2 plus 1, 3. Okay, so irrespective of addition or subtraction, error is only added. Go next slide. So error for multiplication or division operation. When measured values multiply or divide and the fractional uncertainty to divide determine the fractional uncertainty of the result. So if y equal to ab by c, then delta y by y equal to delta a by a plus delta b by b plus delta c by c. Here in this formula, we can see that irrespective of whether it's multiplication or division, the formula remains the same. And delta y by, okay. And here in this formula, we neglect the term delta a into delta b by ab because it's extremely small. So the value, the result we get, it will be extremely close to the given result. So with the example x equal to 15 plus or minus 2 into 9 plus or minus 1. Using a relative uncertainty delta x by x equal to 2 by 15 plus 1 by 9, 0.24 bar. So again x equal to 15 into 9, without the error 135, and delta x by x is 0.24 bar. We take x to the other side, so we get delta x, and add with x we get the final result. Bro, next slide. So constants, when multiplying or dividing by the constant, uncertainty again multiply or divided by the same factor. The constant does not influence that much. So 5 into 5.25 plus or minus 0.03. So you can see that the error is directly multiplied with the constant 0.15. Bro, next slide. So for powers, extended version of multiplication rule, if y equal to a per n, delta y by y equal to mod of n into delta a by a. So in the example, if we take y equal to 2 plus or minus 0.2 the whole cube, so using the formula we take delta y by y, relative uncertainty equal to mod of 3 into 0.2 by 2 equal to, so 0.3, delta y equal to 0.3 into 2 cube, that is y equal to 0.24. So y equal to 2 cube plus 0.24, we get y equal to 10.4. But if we directly substitute the given values, that we directly find 2 plus or minus 0.2 the whole cube, we'll get almost like y equal to 10.68 or y equal to 10.2. So it gives us approximate values. Next slide. So here problems, few problems. Length and breadth of a rectangle are 5.7 plus or minus 0.1 centimeter and 3.4 plus or minus 0.2 centimeter. Calculate the area. So area from a multiplication formula, we can directly use a multiplication formula to find the result. See here area equal to a plus or minus delta a equal to L into b. So first we are finding the initial area without error 19.4 centimeter square. Then we are using the relative uncertainty formula delta a by a equal to delta L by L plus delta b by b. And find substituting the given values, we are finding delta a, and then we are finding the area a equal to 19.4 plus or minus 1.5 centimeter square. Go next slide. So another problem is to temperature of a two body measured by thermometer are at T1 20 plus or minus 0.5 centimeter degree Celsius, T2 50 plus or minus 0.5 degrees Celsius. Calculate the temperature difference. So we use this addition or subtraction formula, naturally T equal to T2 minus T1. You can say irrespective of addition or subtraction, we can directly add the error. So 0.5 plus 0.5 will get 1, and on subtracting 50 minus 20 will get 30. So bro, next slide. So in the above formulas, you can see that if you will be neglecting few terms, so we'll be only getting the approximate values. Now to get approximate values, we can use different formulas. In the above formulas which I mentioned will be used in mathematical problems, but these formulas will be used in physics generally. The problems based on these formulas will be given in Saiteja. These formulas are derived using differentiation. Example, take fourth formula, addition subtraction, z equal to x plus or minus y. In those formulas you can directly add the error, but here we are delta z equal to root over delta x square plus delta y square. Here we are negating the term delta x into delta y. Usually used in the physics laboratory problems like lens or other vernier caliper, we are using it. Bro, next. So there's an extended version of the previous problem. The above formulas which are given, you can find that they have a condition to be used. So the function can only contain one or two operations. The other operation cannot be contained. So we need a general formula to find for a function which contains all the operation with respect to addition, subtraction, multiplication, etc. So this formula is derived using Taylor series, which will be given by Shashi Kumar. Shashi Kumar will carry on. Thank you, sir.
Good morning, sir. Yes, good morning, sir.
Very good morning, Shashi Kumar.
Hello, everyone. Today I am going to present on function of single variable and multivariable. Next slide, Blue. Hello. Let us see the function of a single variable that is dependent on a single independent variable x. Let us assume that here x bar is approximation of x. So here we would assess the effect of discrepancy between x and x bar on the value of function. So we would like to estimate the approximation of the function, that is delta f of x bar equal to mod of f of x minus f of x bar. Next slide, bro. Here we can here we can do approximation, but we do not know what x it is. But we know that x is.
Shashi Kumar, steam your camera, Shashi Kumar.
Sir, I'm seeing, but my camera is not working, sir.
Okay, no issues. Carry on.
Okay, sir. We can do approximation, but here we do not know x. So we use some formula to calculate delta f of x bar. In question, they will give x bar. We know that x bar is close to x. So here we use by using Taylor series formula, that is f of xi plus 1 to f of xi plus f dash xi into f of xi plus 1 minus xi plus f double dash xi by 2 factorial into x I plus 1 minus xi whole square. Like this, continue. Now we use the formula to calculate delta f of x square. So we can find f of x. We know that x and x bar are near. By using the above formula, we can find f of we write f of x. So f of x equals to f of x bar plus f dash into x bar into x minus x bar plus continuously. We are substituted x at the place of xi plus 1 and x bar at the place of xi, since they are near. Next slide, bro. The function we are solving was of first order, so we omit second or higher order because they are negligible. So after doing so, the equation becomes f of x minus f of x bar is approximately equal to f dash x bar into x minus x bar, which can also be written as delta f of x bar equals to mod of f dash x bar into delta x. Next slide. Hello. As I said earlier, delta f of x is equal to mod of f of x minus f of x bar. This represents the estimate of error of the function, and delta x bar represents the error in x. So the above equations provide the options to solve f of x, to find error in f of x. So now we solve one problem. In the given problem, x bar equals to 2.5 with an error delta x bar equals to 0.01. So we estimate the error in the function where the function is f of x equals to x cube. Next slide. Here, by using the formula, we have to solve by formula delta f of x bar equals to here delta 3 into 2.5 whole square into 0.01. Here we got f of 2.5 equals to 15.625, but we have to find f of x. So after solving, we got error equals 0.1875. We got the value 15.625 plus or minus 0.1875. Now after solving this, we get 15.437 and 15.8125. Sorry. To cross check this, we simply put x equals to 2.49 and 2.1551 in the place of x, so that we can know what we have calculated is right or not. After putting 2.49, we get 15.4382 and 2.51 we get 15.8132. This is close to the values we have got earlier. The change in the values is because we have omitted the second order and higher order values, so we have got the error. Next slide, bro. Here now we see the graphical depiction of first order error propagation. Here the graph is plotted between f of x and x. Now the curve represents y equal f of the function. It represents the function. On x-axis we plotted x bar and x. Now we have to draw tangent to the function. Curve. Now we are going to project x and x bar on the given tangent which were on the curve. The projection which fall on the y-axis is known as estimated error, and true error is with respect to the curve. The projection with respect to curve is known as true error. Next slide. Hello. Next slide. Now let us see the for the more than one variable case. We have to do this with the multi-variable version of the Taylor series. Let us say that we have two independent variables that are u and v. Now we can write the formula as f of u I plus 1 v I plus 1 equals to f of u ui vi plus partial derivative of f with respect to u into ui plus 1 minus ui. This continues on. Here also we are going to drop all second order and above order terms because they are negligible, and the final formula we get is f of these all these all partial derivatives are evaluated in the base point. So we will get the next formula as delta into f of u bar in u bar v bar equals to mod of derivative of f with respect to u into del of u bar plus derivative of f with respect to v into del of v bar. Next slide, bro.
Sigmar, how? Yes, go back to the last slide, Sanjay.
Yes, sir.
Sasikumar, the number of slides, how many slides still you want to present?
And only next slide, sir.
Only next. Why you firstly, this is what you made or it was copied from some other? Beware of my English. What is this?
Sorry, sir. I was yes,
Okay, okay. Go to
mistakenly copied, sir. Sorry, sir. I will not
No
intend.
issues.
Okay, sir. Next slide.
Go to the next slide.
Now we look at the. This is for more than two variables case. We have here up to n variables independent, which are independent. So the formula here we get sir, L of f of x1 bar x2 bar up to xn bar equals to partial derivative of f by f with respect to x into del of x1. So, continues. Thank you, sir. Sai will continue. Next.
From the class members.
Okay.
Yes, Sai. Sai Teja. Sai Teja. Yes, how long you will take, Sai Teja? Sai Teja.
So it will take 5-6 minutes.
5-6 minutes. Do you have any classes, subsequent classes?
Yes, we have classes.
You have classes, right? 11:30, you have any classes?
Yes, sir, we have machining class.
Then okay, we will continue Sai Teja in the tomorrow's lecture, Sai Teja. Pranav and Sai Teja, you both you present and you start the session, tomorrow's session, and we will continue with fifth batch.
Yeah, okay.
Okay, thank you. You plan accordingly. We'll start sharply at 11:30, and you plan accordingly. There is 8 people has to present within 50 minutes. Okay,
Okay,
thank
sir.
you. We'll meet tomorrow 11:30.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.